We've learned a little bit about gravity. We've learned a little bit about electrostatics. So, time to learn about a new fundamental force of the universe. And this one is probably second most familiar to us next to gravity, and that's magnetism. Magnetism. Where does the word come from? Well, they actually, I think several civilizations, I'm no historian, found these lodestones, these objects, magnetism. These objects that would attract other objects like it, other magnets, or would even attract metallic objects like iron, ferrous objects. And they're called lodestones. That's, I guess, the Western term for it. And the reason why they're called magnets is because they're named after lodestones that were found near the Greek province of Magnesia. Magnesia. I actually think the people who lived there were called Magnetes. But anyway, that's you could Wikipedia that and learn more about it than I know. But anyway, let's focus on what magnetism is. And I think most of us have at least a working knowledge of what it is in terms, we've all played with magnets and we've dealt with compasses. But I'll tell you this right now, what it really is pretty deep. And I think it's I don't think anyone has, we can mathematically understand it and manipulate it and see how it relates to electricity. We actually will show you that the electrostatic force and the magnetic force are actually the same thing, just viewed from different frames of references. So I know all of that sounds very complicated and all of that. But in our classical Newtonian world, we treat them as two different forces. But what I was saying is, although we're kind of used to a magnet, just like we're used to gravity, just like gravity is also fairly mysterious when you really think about what it is, so is magnetism. So with that said, let's at least try to get some working knowledge of how we can deal with magnetism. So we're all familiar with a magnet. I didn't want it to be yellow. I could make the boundary yellow. No, I didn't want it to be like that either. So if this is a magnet, we know that a magnet always has two poles. It has a north pole and a south pole. And these were just labeled by convention because when people first discovered these lodestones, or they took a lodestone and they magnetized a needle with that lodestone, and then that needle they put on a cork in a bucket of water, and that needle would point to the Earth's north pole. They said, oh, well, the side of the needle that is pointing to the Earth's north, let's call that the North Pole, and the point of the needle that's pointing to the South Pole, the point of the needle that's pointing to the Earth's geographic south, we'll call that the South Pole. Or another way to put it, if we have a magnet, the direction of the magnet, or the side of the magnet that orients itself, it's allowed to orient freely without friction, towards our geographic north, we call that the North Pole, and the other side is the South Pole. And this is actually a little bit, obviously we call the Earth, we call the top of the Earth the North Pole. This is the North Pole, and we call this the South Pole. And there's another notion of magnetic north, and that's where, I guess you could kind of say, that is where a compass, the north point of a compass, will point to. And actually, magnetic north, it moves around because we have all of this moving fluid inside of the Earth and a bunch of other interactions. It's a very complex interaction. But magnetic north is actually roughly in northern Canada. So magnetic north might be here. So that might be magnetic north. And magnetic south, I don't know exactly where that is, but it can kind of move around a little bit. It's not in the same place. So it's a little bit off the axes of the geographic North Pole and the South Pole. And this is another kind of slightly confusing thing, is magnetic north is kind of the geographic location where the North Pole of a magnet will point to, but that would actually be the South Pole of, if you viewed the Earth as a magnet. So if the Earth was a big magnet, you'd actually view that as the South Pole of the magnet, and the geographic South Pole is the North Pole of the magnet. You could read more about that on Wikipedia. I know it's a little bit confusing. But in general, when most people refer to magnetic north or the North Pole, they're talking about the geographic north area. And the South Pole is the geographic south area. But the reason why I make this distinction is because we know when we deal with magnets, just like electricity, or electrostatics, but although we'll show a key difference very shortly, is that opposite poles attract. So if this side of my magnet is attracted to Earth's north pole, then Earth's north pole, or Earth's magnetic north, actually must be the south pole of that magnet, right? And vice versa. The south pole of my magnet here is going to be attracted to Earth's magnetic south, which is actually the north pole of the magnet we call Earth. Anyway, I'll take Earth out of the equation because it gets a little bit confusing, and we'll just stick to bars because that tends to be a little bit more consistent. Let me erase this. There you go. I'll erase my magnesia. I wonder if the element magnesium was first discovered in magnesia as well. Probably. And I actually looked up milk of magnesia, which is a laxative, and it was not discovered in magnesia, but it has magnesium in it. So I guess its roots could be in magnesia if magnesium was discovered in magnesia. Anyway, enough about magnesia. Back to the magnets. So if this is a magnet, and let me draw another magnet. Actually, let me erase all of this. When I go on the tangents, alright. So let me draw two more magnets. So that's one magnet. That's another magnet. We know from experimentation when we were all kids, this is the North Pole, this is the South Pole, that the North Pole is going to be attracted to the South Pole of another magnet. And then if I were to flip this magnet around, it would actually repel. Two north-facing magnets would repel each other. And so we have this notion, just like we had in electrostatics, that a magnet generates a field. It generates these vectors around it that if you put something in that field that can be affected by it, so there'll be some net force acting on it. So actually, before I go into the magnetic field, I actually want to make one huge distinction between a magnet and or between magnetism and electrostatics. Magnetism always comes in the form of a dipole. What does a dipole mean? It means that we have two poles, a north and a south. In electrostatics, you do have two charges. You have a positive charge and a negative charge. So you do have two charges, but they could be by themselves. You could just have a proton. You don't have to have an electron there right next to it. You could just have a proton, and it would create a positive electrostatic field, right? And our field lines are what a positive point charge would do, and it would be repelled. So you don't always have to have a negative charge there. Similarly, you could just have an electron, and you don't have to have a proton there. So you can have monopoles. These are called monopoles, where you just have one charge when you're talking about electrostatics. But with magnetism, you always have a dipole. If I were to take this magnet, this one right here, and if I were to cut it in half, somehow, miraculously, each of those halves of that magnet will turn into two more magnets, where this will be the south, this will be the north, this will be the south, and this will be the north. And actually, theoretically, I've read, my own abilities don't go this far, there could be such a thing as a magnetic monopole, although it has not been observed yet in nature. But so everything we have seen in nature has been a dipole. So you could just keep cutting this up all the way down to if it's just one electron left, and it actually turns out that even one electron is still a magnetic dipole. It still is generating, it still has a north pole and a south pole. And it actually turns out all magnets, the magnetic field is actually generated by the electrons within it, by the spin of the electrons. And that, when we talk about electron spin, we imagine, some little ball of charge that's spinning. But electrons are, it's hard to, they do have mass, but it starts to get fuzzy whether they're energy or mass, and then how does a ball of energy spin, et cetera, et cetera. So it gets very almost metaphysical. So I don't want to go too far into it, and I don't think you really can get an intuition. It is almost, it is a realm that we don't normally operate in. But even these large magnets you deal with, the magnetic field is generated by the electron spins inside of it, and by the actual magnetic fields generated by the electron motion around the protons. Well, I hope I'm not not overwhelming you. And you might say, well, how come sometimes a metal bar can be magnetized and sometimes it won't be? Well, when all of the electrons are doing random different things in a metal bar, then it's not magnetized because the magnetic spins or the magnetism created by the electrons are all canceling each other out because it's random. But if you align the spins of the electrons and if you align their rotations, then you will have a magnetically charged bar. But anyway, I'm past the 10-minute mark, but hopefully that gives you a little bit of a working knowledge of what a magnet is. And in the next video, I will show what the effect is. Well, one, I'll explain how we think about a magnetic field, and then what the effect of a magnetic field is on an electron, or not even an electron, on a moving charge. See you in the next video.